Welcome everybody to the talk Hacking a Professional Drone. My name is Nils Rodday and I'm from Germany. I've very recently been a master student at the University of Twente, where this talk actually originates from. So I did my master thesis at the University of Twente, and during that master thesis was done during an internship at KPMG. And saying so, of course, today I'm just speaking on my own. I'm not speaking on behalf of my former employer and not on behalf of my current employer. So it's just all my opinions here that I'm stating. The work was done in collaboration with a drone manufacturer. So the drone manufacturer provided us the device to look into the security of the device, and we in return provided our insights and told the manufacturer which vulnerabilities exist and how to fix them. So essentially the content today you will see is originated from that master thesis, and it will contain the vulnerabilities. I will show the attacks and so on. So the goal of the talk today is to give you an insight into the security of unmanned aerial vehicles. This is actually how those things are called, and to show you that those professional UAVs are not secure as you might think. I will quickly introduce the agenda. So first, I'm starting with the setup itself. I'm jumping right into the technical content and into the topic because there are just 25 minutes. So it will be quite technical then. I will go over the attacks. So I will tell you which attacks we mounted on the UAV and which did work out. Then I will perform the live demonstration, so I'll show you that actually the things we discovered are working and you can control the UAV in the end. We'll talk about the remediation and the impact, and afterwards I will talk about lessons learned. So basically, how can you make sure that such vulnerabilities do not occur in future setups anymore. And after my talk, there will be a short Q&A session, so you're welcome to ask questions. As I said, I will jump right into the topic. So what actually differentiates a professional UAV from a normal consumer UAV you could buy at Tesco or Media Market or any supermarket? It's way more expensive. That's the first thing. So you pay around 25 to 30,000 euros for it, which roughly is $30,000 to $35,000 US American dollars. So it's a little bit more in Singaporean dollars then. It can carry up to 3 kg of payload, which is roughly 7 pounds of payload, which is really a lot. If you compare it to consumer UAVs, they can barely carry anything. So this is really able to lift a lot of heavy weight. Up to 45 minutes of endurance, so the batteries are quite strong, and you can therefore use it for different use cases than the consumer UAVs. And as I said, it's used for a lot of different use cases. So it has advanced capabilities and advanced features compared with those recreational or consumer UAVs. You can actually steer it via an application. You can have automated flight. You can change parameters from 2 kilometers away from the UAV and operate it from a distance of 2 kilometers, which is quite far from the UAV. There are a lot of add-ons existing, so you can, for example, add, of course, cameras to it to perform, for example, surveillance tasks, or you could attach sensors for fire departments to measure gas toxins or spot wildfires with a camera. There are also other enterprises using these devices for a lot of other use cases. So those are the specifications. Now I'll talk about the setup itself. So the setup contains essentially 4 parts here. On the right side, you can see the UAV itself, which is obviously this thing. Then there is the telemetry box, which is here on the table. So you can later have a look. There is a manual remote control, which is that one. Then there is a tablet, which is that one, containing the flight planning software. Throughout that tablet via that tablet you can actually steer it, or you can also use the manual remote control. The manual remote control is connected to the UAV via 2.4 gigahertz link. Therefore, it just has a range of 100 meters, and it's quite limited because you want to steer the UAV from further away than 100 meters, right? So there is another link existing, that is a telemetry link, which consists out of two physical links. The first one is a Wi-Fi link connecting the tablet to the telemetry box here. And the second one is an XBee link connecting the telemetry box to the UAV itself. And this link has a range of 2 kilometers, up to 2 kilometers. So the important part here is there are two communication and control links. The first one is the manual remote control, and the second one is the telemetry link that consists, again, out of two physical links. And there's also a video link, but we are not going into details with the video link today. Now you can see the blue parts are the data flows, so you can see that the telemetry link is actually one logical link, while the remote control is the other one. Okay, so our research focused on the telemetry link because of two reasons. First, extended range, and second one, advanced capabilities and advanced features. And I will first talk about the Wi-Fi link. So as you might see, there is written WEP as an encryption scheme. You might know that this encryption scheme is weak, so it shouldn't be used. And the attack you can mount is that you de-authenticate the original user. So you de-authenticate through the access point the original user by using by sending de-authentication packets, and you connect your own tablet with your own flight planning software to the access point, and you would already gain full control of the UAV. You can see the passphrase, which is actually used in that setup, so you could then connect your own flight planning software to that UAV, and you already got full control. But as I said, this is Wi-Fi, and WEP is not really something new, so that's known. It's certainly a vulnerability in this setup, but it's already known. And also this attack is quite limited because Wi-Fi has only a range of also roughly 100 meters because it's also, in this case, using 2.4 gigahertz. Which is why we focused on the other link then. This is an XBee link, XBee 868LP. LP stands for low power. And this link, as I said before, reaches up to 2 kilometers. So you can actually control the UAV from much further distance. There you can see the chips itself. The chip is in here, so in the UAV, and the other chip is here in the telemetry box. And the telemetry box is then forwarding the communication via Wi-Fi to the flight planning software on the tablet. And as we thought about how to get into that channel, the first thing we thought about is software-defined radio. And we tried a bit with software-defined radio, and it turned out that you actually need quite a lot of resources for software-defined radio. It's quite expensive to do, which is why we then focused on we might just buy a chip itself and then use a third chip as an attacker to actually connect to that communication channel. And what do you need to connect to that communication channel is actually the address that is written right on the chip. So within the red rectangle on the left side, you can see that there is an address written. It's really small here. However, this address is 16 characters long, and it's made out of hex characters. So there are a lot of combinations. And we thought about brute force, but there are too many combinations. And we actually found a better way simply by having a look at the instruction manual. So we read the manual, or I read the manual in this case, and then I came up with 3 features here that you can use and combine to actually compromise the security of that channel. So the first feature is that you do not only have to use transparent mode that is used in this setup, but the chip also supports another mode called API mode. And in API mode, you can send API frames. So not only just the payload, but the payload is wrapped into a packet, and you can specify the destination address, for example, so the destination address of this chip or of the other chip, as an attacker on your own. Otherwise, in transparent mode, the destination address is always taken by the chip itself, and the payload is added itself by the chip. So you switch to API mode, and then you are able to send the packets you would like to send. You are able to craft your own packets instead to rely on the chip to craft the packet. There is another feature, and that is really simple. It's called broadcast. And this broadcast feature allows you, which can only be used in API mode, to send one packet out instead of brute forcing through all the addresses to get acknowledgements back from all participants within the network. So you send with one of those chip here, first you switch to API mode, then you send a broadcast out to the network, you receive acknowledgements back, one from the UAV, one from the telemetry box, you extract the sender's addresses because the address of the sender is inside of that packet, right, the acknowledgement packet. You extract those addresses, and then you know the participants within the network. So you know who the UAV is, which address it has, and you know the telemetry box. And then there is a third feature that you can use to remotely change the address of another chip, and that is called remote AT command. So with the attacker's chip in API mode, you can craft a frame that tells another chip to actually change its destination address. So for all future communication, the chip will not send its traffic anymore to the original address, which means telemetry box to UAV and the other way around. But instead, the UAV and the telemetry box will then send all traffic to the attacker, right? With the previously recorded sender's addresses from the acknowledgements, you can then forward the communication between the two participants in the network, and you effectively mounted a man-in-the-middle attack. So that is essentially not a bug, it's a feature of the system, because those chips are used in mesh networks. And in mesh networks, you need to be able to switch the communication route quickly because there could be congestion on one channel, right? So you would like to switch the communication route. In our case, this is not really good because if you change the communication route of a one-to-one communication here, you essentially reroute the communication, and therefore it's possible to mount the man-in-the-middle attack. I will now show you the man-in-the-middle attack. So you can see here the telemetry channel in green within that drawing or picture. And there's the attacker's chip, which is that chip right here in front, so you can later have a look. And first you switch to API mode, you send a broadcast packet, you receive acknowledgements back, you extract the sender's addresses from those acknowledgements, then you send a remote AT command to the remote chips, change their addresses to your address, and for all future communication, the traffic will be sent to you as an attacker. And if you would like to, you can send another command that is a write command. This command would persist the changes on the storage of the chip, but this is optional because if you would not send it, like I will show it in my demonstration here, the old address is actually restored if you unplug the battery and you plug it back in. So nobody could even determine when the drone was taken down for some reason afterwards and somebody performs analysis on the drone, what did happen, why did it fly away or something. Nobody would be able to determine what actually happened because the old address is restored. Okay, then now you can see the communication route after the attack happened. So the communication is now routed from the tablet to the telemetry box and now to the attacker's chip, and then to the UAV and the other way around. So the attacker can actually read all the traffic, but he's just not able to understand the traffic yet, right? So there are just some hex chars sent through the network channel, but we don't know yet what those hex chars mean. And to figure that out, we had a look at the Android application here. So there are 4 steps essentially. You perform, you rename Android APK to zip, then you extract the zip, then you use a tool called dex to jar. You can actually transform those dex classes to a jar file, and then you can use a tool called JDGUI to actually visualize the whole thing. And that's what you see here. You see a file tree with a lot of files, with a lot of class files, and we went through all of those methods, and one method in particular raised our attention. That is a method called send data code command. And this method starts with a static preamble here. So 36, 27, or it's 87, and so on. And then it's followed by 3 parameters. So 3 param-byte parameters. They're actually the same. It's the same variable written here. We transformed them from decimal to hexadecimal characters, and there you go. This is exactly what you see when you monitor the channel and what you see when you perform the man-in-the-middle attack. So now we were able to map the hexadecimal commands sent through the channel to commands within the Android application, and we knew basically what the commands are. So now you can watch the channel, you can try different features of the UAV, and you will be able to figure out what those features are. I will show in the live demonstration here the start engines command, so that you can see that the attack is actually working, and the UAV starts its engines, and you can inject basically any command the original flight application can perform, and you can inject any command to that communication channel and perform exactly the same action as an attacker from a distance of 2 kilometers. Okay, then I will go over now to the demonstration. So the demonstration has 2 parts. First of all, I will just run the Python script that performs those 4 tasks: switch to API mode, send broadcast packet, extract sender's addresses, send a remote AT command, and then change those addresses to perform the man-in-the-middle attack and forward the communication between the 2 parties. So for now, the communication is working from UAV to telemetry box to the Android application. And if we run the script here, we can see that there are a lot of packets now transmitted from the UAV to the attacker's chip to the telemetry box, and then the traffic is going to the tablet. You can see that here. So now all the traffic is running through the XBee chip here. So that was the first part. I will now show the command injection attack, so that we are actually able to inject commands to the communication channel and make the UAV do something. Therefore, I need the other computer again. Could you? Yeah. Okay. So what you can see here now is actually the original software from the manufacturer of the chip that is used from this XBee chip. It's called XCTU. And I saved a couple of packets here. So the first packet here that we will send is the command start engines. And the text that is highlighted right now is the address of the chip of the UAV, because we obtained the address before by extracting the sender's addresses from the acknowledgement of the broadcast packet, right? So we actually know the address, and therefore it's inserted here. And this here, what you can see here, that's the payload we are sending to the chip. So so this is the static preamble. And the last 6 hex chars here, 898989, this is the command for start the engines. Okay. And we'll just loop infinitely through this command and start the sequence. And now this chip is sending out the data to the UAV, and the UAV is receiving this data, and then is actually receiving the data and is performing the action. Okay. I will stop that and shut it down manually. So what you did see now, it stopped shortly, is because I'm using a static power source here instead of a battery. And with a static power source, this power source isn't able to provide enough energy if all 8 engines are starting at the same time, which is why if too many amps are drawn from the power line, then the voltage breaks down, which is why it's shortly stopped and started up again, because it's still receiving the command start engines, and then it's starting up again. Yeah, so this essentially is the demonstration part. I will simply unplug the UAV, because now the engine is in a safe state because it got a low voltage. I will talk next about remediation. So how can we actually mitigate the discovered vulnerabilities here. So an attacker is able to inject a command and make the UAV do whatever he likes it to do. And the first remediation is quite easy. You could use the native XBee encryption that is already provided on the chip. You would simply have to switch it on and insert a key to provide to use symmetric encryption between the telemetry box and the UAV. This would disallow the attacker to send a remote AT command and secures therefore the data on the XBee channel. So as I said, it prevents remote AT commands and it therefore also mitigates the man-in-the-middle attack. However, the manufacturer is not able to use this mitigation because additional encryption on the chip decreases the bandwidth and it increases the latency of the chip, which is why he can't use it and why we suggested another countermeasure. So what we suggested then was, okay, if the encryption increases the latency too much, then you can simply outsource the encryption, so to speak, to a second separate chip, and you put another chip in front of the XBee chip, which does the encryption. This would then ensure that the data is encrypted by going through that channel. However, it would not prevent remote AT commands from happening because those remote AT commands are sent directly to the XBee chip, and the XBee chip would still perform like this change of address, although the attacker wouldn't be able to read the data because it's encrypted, right? It does not mitigate the man-in-the-middle attack, but it ensures confidentiality, right? So you cannot read the data, but you can still, for example, set random values to destination addresses and therefore perform a denial-of-service attack. And the third thing we suggested is application layer encryption. So you could use encryption from the software running on the flight, so the flight planning software running on that tablet to the UAV. And you would also not prevent remote AT commands, and it would not mitigate the man-in-the-middle attack on that XBee channel. However, it would also ensure confidentiality. So somebody would still be able to perform a denial-of-service attack if you would set it to random values, but he would not be able to inject a packet and actually take over the UAV, which he is able to do now. So what is the impact of this research? What you can do here is with equipment worth of $40. Basically, it's just the XBee chip you need and a serial adapter cable to connect it to your computer. You can inject packets to a UAV that is worth 25,000 euros, which is currently in use by a lot of entities. And you can basically take this device over. And other manufacturers are possibly using the same setup. So I contacted a lot of manufacturers. They told me, yes, we are using XBee chips. However, they didn't want to tell me if they are using native XBee encryption or not. And it's not only limited even to UAVs and UAV setups, but also to all kind of IoT devices that are using XBees in general, because if you are not aware that these features are existing within the chip and you're using it just like in this setup in transparent mode from A to B without encryption, then anybody would be able to perform this attack and mount a man-in-the-middle attack and read your traffic, redirect it, and inject packets. So there are quite simple lessons learned then. You should use encryption on the XBee layer. You should use strong encryption on the Wi-Fi link, right? And you should also alter your passphrases, because the passphrase you have seen there is not only used in this setup, but it's used in all the setups. So even if you would use strong encryption, you could simply enter the password once you know it for your own setup. So you should obviously alter the passphrases for different setups. And the third thing is, what actually this manufacturer did right from my point of view, you should test your product. You should go to somebody, give it to somebody, perform some research on it, and see if there are security vulnerabilities, and this manufacturer is now able to fix them and issue a new release and have a secure device in the end. I'd like to thank a couple of people. So, as I said, the research was done at the University of Twente. And there I had two supervisors, Professor Dr. Eiko Pras and Ricardo de Oliveira Schmidt. And at KPMG, my supervisors, Ruud Verby and Mathieu Pargues. And especially I'd like to thank two other people, Artul, who helped me with the mapping part from hex to decimal and the commands essentially, and Annika, who helped me setting up the demo presentation, rehearsing and so on. Those are my contact details. If you have any questions, I'd be happy to answer them. And just drop me a mail or just give me a message on LinkedIn. That's it, I think. Now we have time for a Q&A. Thank you. Are there any questions? Yeah.
So you mentioned the potential for a denial of service attack against it. Was that something where, did you test any of that to where, is it just keeping the drone from leaving the ground, or what's the potential for it that's already in flight?
So denial of service, you mean, for example, if it's, you imagine it's, for example, 1.5 kilometers out, right? And you cannot control it with a manual remote control anymore because it's more than 100 meters. So you would definitely rely on the telemetry channel then, right? You can just perform this denial of service attack and you would not see anything anymore in this application because there's no data anymore received by this application. So it'd simply be blind and you don't know where your device is and what it's doing and you cannot regain control. So first of all, I think it would simply go on its automated flight. And if it's in the end of its automated flight, it will stay up in the air and at a certain point go back in a safe state and then try to land. Yeah?
You mentioned some organizations that are using that particular model. What sort of services or who are they?
So, for example, there are companies using these devices for power line inspections and so on, so all kinds of use cases for the private sector. And there are, for example, police departments using that for surveillance or fire departments using that for spotting wildfires or performing gas analysis and stuff. Yeah? Well, XBee is just a chip, so you can use it basically for every setup to transmit data. In every setup, what you would like to do, the chip just costs $20, so it's really cheap, and you can transmit data from a distance of 2 kilometers, so it's used in a few setups, yeah. Okay, then, thank you, and I'll be at the reception, so if you have any more questions, just approach me. Thank you.